Welcome to the new era of video creation with Bayozi. This is our new series on teaching deep learning. Today we will discuss the transfer learning in computer vision. Here are the contents. Transfer learning is a powerful technique in machine learning where knowledge gained from solving one task is used to help solve a different but related task. In computer vision, transfer learning often involves using a model pre-trained on large datasets, like ImageNet, and fine-tuning it for a different task, often with limited data. The core idea behind transfer learning is that certain features learned by a model for one task are useful for other tasks as well. For example, a model trained on ImageNet, which consists of millions of images across thousands of categories, learns low-level features like edges and textures that are useful for many vision-related tasks. By leveraging these pre-trained features, we can save on computational resources and avoid the need for large labeled datasets. In computer vision, tasks like image classification, object detection, and semantic segmentation benefit greatly from transfer learning. This approach enables faster training and better performance on smaller datasets. Transfer learning is particularly useful because it addresses several common challenges in computer vision: training time and computational resources. Training deep neural networks from scratch requires significant computational resources and time. Using a pre-trained model can dramatically speed up the process. Limited labeled data. Obtaining large amounts of labeled data for training can be expensive and time-consuming. Transfer learning allows models to perform well even with limited labeled data for a new task by leveraging the knowledge from a related task. Model performance. When a model is pre-trained on a large, diverse dataset like ImageNet, it learns features that are highly generalizable to other vision tasks, thus improving performance on new, specialized tasks. Fast prototyping. Transfer learning allows researchers and practitioners to quickly test models on new problems. By fine-tuning a pre-trained model, they can focus on problem-specific aspects rather than starting from scratch. The general process of transfer learning involves several key steps. Pre-trained model. Begin with a model that has been trained on a large general-purpose dataset like ImageNet. This model has already learned useful features, such as edges, textures, and shapes, that are applicable to many vision tasks. Replace final layers. Since the original model was trained for a different task, e.g., object classification on ImageNet, we usually replace the final classification layer with a new one that corresponds to the classes in our specific task. Fine-tuning. Fine-tuning involves training the model on the new task, typically with a smaller learning rate, to adjust the weights of the network to the new problem. This allows the model to adapt the learned features to the new data without forgetting the general features. Performance monitoring. As fine-tuning progresses, the performance should be monitored, and hyperparameters may need to be adjusted. If the model overfits, techniques like early stopping or regularization might be applied. When performing transfer learning, choosing the right pre-trained model is important. Some of the most common models that have been pre-trained on ImageNet include VGG16, a simple and deep architecture that is widely used but relatively computationally expensive. ResNet, known for its deep residual connections that allow for the training of very deep networks, making it more powerful for complex tasks. Inception, a more computationally efficient model that combines multiple filter sizes in a single layer. MobileNet, a lightweight model designed for mobile and embedded devices, ideal when computational resources are limited. These models are widely available in popular deep learning frameworks like TensorFlow and PyTorch, and they can be easily fine-tuned to new tasks. Choosing the right pre-trained model depends on factors like task complexity, available computational resources, and the required speed or accuracy. Fine-tuning is a critical step in transfer learning, and it can be performed in several ways. Freezing layers. In many cases, the early layers of a pre-trained model capture basic features like edges and textures, which are applicable across various tasks. You can freeze these layers, i.e., prevent their weights from being updated, and only train the later layers, which are more task-specific. Gradual unfreezing. Another strategy is to start by training only the final layers and then gradually unfreeze earlier layers. This allows the model to learn task-specific features while retaining the useful low-level features from the pre-trained model. Learning rate adjustments. Since the early layers already have useful features, we typically use a lower learning rate for these layers and a higher learning rate for the newly added layers. This prevents the model from distorting the learned features too much during fine-tuning. Data augmentation. To prevent overfitting, data augmentation techniques, e.g., random cropping, flipping, or rotating images, can be used to artificially increase the diversity of the training data. Transfer learning can be categorized into different types, depending on the relationship between the source and target tasks. Domain transfer. This occurs when the source and target tasks are similar, but the data distributions are different. For example, transferring a model trained on images of cats and dogs to a task involving images of other animals. Task transfer. This involves transferring knowledge between different tasks in the same domain. For instance, using a model trained for object classification on ImageNet and fine-tuning it for object detection. Inductive transfer. In inductive transfer, the source and target tasks have different labels. For example, training a model to recognize objects in a general category, then fine-tuning it for a specific subcategory. Transductive transfer. In transductive transfer, the tasks share the same labels, but the distributions of data are different. For instance, using a model trained on outdoor images to adapt to indoor images. In the context of object detection, transfer learning is particularly useful because it involves both localization, finding where objects are in an image, and classification, identifying the objects. Some of the most popular object detection models are Faster RCNN, a two-stage detector that first generates region proposals and then classifies them. YOLO, You Only Look Once, a one-stage detector that predicts bounding boxes and class labels directly from the image. By leveraging transfer learning, we can fine-tune a pre-trained model, e.g., on ImageNet or COCO, for specific object detection tasks. This is highly beneficial when dealing with small datasets, where training from scratch would be inefficient. Transfer learning helps adapt the model to detect specific objects or categories that the original model wasn't trained for. Semantic segmentation is a task where each pixel in an image is classified into a category. Models like fully convolutional networks, FCN, UNet, and DeepLab are widely used for segmentation tasks. These models typically begin with a pre-trained CNN, such as ResNet, to leverage the learned features from large datasets. By using transfer learning, the general features learned by the pre-trained model, e.g., edges, textures, and object boundaries, can be reused for pixel-level classification. Fine-tuning helps the model adjust to the new segmentation task, which is typically more specialized and requires precise pixel-wise predictions. When using pre-trained models for transfer learning, there are two primary approaches. Fine-tuning. This approach involves updating all layers of the pre-trained model, adjusting them to the new task. Fine-tuning is more flexible and can adapt the model to a broader range of tasks. However, it requires more labeled data to avoid overfitting. Feature extraction. In this approach, the pre-trained model's layers are frozen, and only the final layers are trained on the new task. This method is faster and requires fewer data, but it might not be as effective for complex tasks that require more task-specific adaptation. While transfer learning is powerful, it comes with its own set of challenges. Domain gap. If the source and target tasks are too different, transfer learning may not be as effective. For instance, a model trained on photographs might not perform well on medical images without significant adaptation. Overfitting. Fine-tuning on small datasets can cause the model to overfit to the new task, especially if the task is highly specialized. Data mismatch. Differences in data distributions, e.g., lighting, background, or object orientations, between the source and target datasets, can make transfer learning less effective. Computation cost. Some pre-trained models, like those based on deep architectures, can be quite large and require considerable computational resources to fine-tune. To get the best results from transfer learning, it's important to follow best practices. Start with pre-trained models. Always begin with a model that has been trained on a large, diverse dataset like ImageNet. This gives the model a solid foundation of useful features. Freezing early layers. Freeze the early layers, which capture low-level features, and only train the later layers. This saves computational time and reduces the risk of overfitting on smaller datasets. Data. Augmentation. Implement data. Augmentation techniques to artificially expand your dataset and improve model generalization. Performance monitoring. Regularly monitor the performance of your model on a validation set and adjust hyperparameters like learning rate, batch size, or layer freezing as needed. Transfer learning has proven to be immensely useful in various real-world applications. Healthcare, medical image classification, and segmentation tasks often suffer from limited labeled data. Transfer learning allows us to use models pre-trained on large image datasets to classify medical scans with fewer annotated images. Autonomous driving. Pre-trained models can be fine-tuned for object detection and semantic segmentation in the context of autonomous driving, where the system needs to understand and react to the environment in real time. Robotics. Robots can leverage pre-trained vision models for tasks like navigation, object recognition, and manipulation, where fine-tuning allows the system to adapt to specific environments and tasks. Security. Facial recognition systems can benefit from transfer learning, where models pre-trained on large, diverse datasets are fine-tuned on specific populations or environments for better accuracy. The future of transfer learning in computer vision is bright. Pre-trained models. Models will continue to evolve, with larger and more diverse datasets enabling even better generalization across tasks. Few-shot learning. One area of significant research is few-shot learning, where models can perform well with very limited data. This would be a huge leap in transfer learning, enabling effective use even in situations with scarce labeled data. Cross-domain transfer. Future research will likely improve the ability of models to transfer knowledge across tasks and domains that are very different from one another, further expanding the applicability of transfer learning. Integration with other AI techniques. Transfer learning will likely be integrated with other advanced AI techniques, such as reinforcement learning and unsupervised learning, allowing models to leverage multiple sources of knowledge. In summary, transfer learning is a powerful technique in computer vision that allows us to apply knowledge from one task to another, improving performance and reducing the need for large labeled datasets. By fine-tuning pre-trained models, we can adapt them to new tasks quickly and efficiently. Transfer learning is widely used across many industries, from healthcare to autonomous driving, and continues to evolve with advances in machine learning techniques and models.